Okay, so I guess, you sent me this link to a Reddit Ask Physics thread, and it says, so the guy like links to a GIF of a balloon inside of a balloon, and they pop the inner balloon with the magnifying glass, like focusing the sun onto the inner balloon, and it pops it. And he kind of says, is it going to inflate, deflate, or stay the same? The outer balloon, will the volume of it change essentially? And if so, how? Yeah, so we had the same initial kind of thought, I think, where, well, it seems like, okay, it's the same volume, essentially, it's just not inside of the inner balloon now. Now it's in the outer balloon.
Right.
So then I read this first comment, and it talks about the pressures involved. And I was like, oh, okay, maybe I didn't really think about this deeply enough. So I think like maybe an easier place to start is if you considered like a bag filled with air, like a trash bag or something, versus a balloon.
Okay.
So I think if you essentially repeated this experiment, but you took like a trash bag and you filled it full of air, and then you took it and put it inside of another one that you filled full of air, not to where they're like super duper, inflated. There's just some air in them. And then you did the same thing. You popped the inner one. I think, there's going to be no change. But the difference here between the trash bag and the balloon is the balloon is kind of, it has like a spring effect. It's compressing the air.
Right.
I guess like the question kind of is, what's the pressure inside of a balloon when you inflate it? Is it the same as atmosphere? Is it less than atmosphere, or is it more than atmosphere? Yeah. So what's your thought there?
I think it has to be more than atmosphere, and it has to balance the elastic strength of the balloon's rubber itself, kind of containing the air. So it's like a combination of atmospheric pressure outside. I'm hesitating now. I'm thinking of something else. That's my first take, but now my brain's going on to other things, so maybe not. But that is my first take.
Yeah, I mean, I think the thing I can say for sure is it's not. Oh, I guess I can't say that for sure, but I'm pretty sure it's not less than atmosphere. Because if it's less than atmosphere, potentially it could be neutrally buoyant, meaning it's just going to stay in one spot. It's not going to go up or down if you let go of it. Or it could become like a helium balloon, float in the air.
Right.
But now I'm weirded out about helium balloons.
Well, okay, let me just, I think we're overthinking it. Like,
okay.
Take a balloon sitting on the desk. It's not inflated. It's just an empty, quote unquote, empty balloon. Uninflated balloon. The atmospheric pressure inside and out is the same.
Right. Yes.
Okay. What do you do to blow up a balloon? You put your mouth on it and blow pretty hard.
Yeah, you got to compress air to put it in.
Yes. So to like right there, I'm like, yeah, it's pressure is higher on the inside than the outside of the balloon.
Right. Okay. I think that's it. Yeah.
Good.
Okay. So
well, how about we pause for a second? Why were we both kind of tripping up on that? Like, it seems really obvious, but we both were like, well, maybe it's the same. Why wasn't it obvious when you think about an inflated balloon in and of itself? I tried to approach it from thinking about forces on either side of the rubber of the balloon, like the latex of the balloon. And when I started thinking about that, I was like, well, I don't really know. Just because it's stretched doesn't mean it's higher pressure. Like if you took a sheet of rubber or latex and just stretched it out in the air, not a balloon, not closed, not tied off or anything, just a sheet stretched, the pressure on either side of that is the same.
Right.
I understand like the forces are your hands stretching the piece of rubber or whatever, like a frame or something like that. But
right. But then I think that's the whole crux of it is in the balloon case, the force, the thing that's expanding it is the air.
Right. Does the balloon know which is the inside and the outside?
Do balloons know things?
Like I'm thinking like topologically, could you like invert the balloon like with the pressure? I don't even know what I'm asking.
I think like your kind of normal thought is just like, oh, I'm just putting air in it from, the outside. Or, it's atmosphere outside and I'm just transferring it inside the balloon. But yeah, if you miss the blowing up part, there's a compression part of it. I mean, I guess like maybe the weird part is even let's say it did have if it had the same pressure inside and outside, when you untied the balloon or you released it, it would still shrink if it was a balloon, right? Because the plastic, the rubber wants to collapse. Or no, maybe that's the whole
I think the rubber would collapse. Like if the pressure was the same inside and out of the balloon, you just tied a knot and that was it. You didn't change the pressure, or somehow you measured the pressure to be equal inside and out, and it was sealed perfectly. And then you unsealed it. I think the sealed and unsealed configuration of the balloon, like what you're saying, like the weight of the balloon itself would be in equilibrium in both situations, and it wouldn't change going from sealed to unsealed, or closed to open balloon.
Okay, so like if somehow you had a balloon that was expanded and there was air inside of it, and magically or by maybe there's some way you could do it, you made the gas inside 1 atmosphere of pressure and the gas outside is 1 atmosphere of pressure, then when you open the balloon, it's gonna just stay the same.
Mm-hmm.
I'm imagining. So I think you could do that. No, you couldn't. I was thinking if you like blew it up and then, like on top of Mount Everest or something, and then you walk down until the outside pressure equals the inside pressure. But I think the outside pressure is also just going to put more force on it as well. Right? Like if you, do you see what I'm saying? Like if you blew up a balloon on Mount Everest,
right?
And then let's say it's 9/10 of an atmosphere or something up there. I actually don't know what it is. I think it's less than that, but whatever it is. And then you walked down until the pressure was equal to whatever it was inside the balloon. Like, well, let's say inside the balloon now it's 1, and then you walk down until you're at 1, so back to sea level.
What's your balloon look like?
Yeah, or is the balloon still at 1 atmosphere, or has it increased in pressure?
I think if the balloon inside and outside pressures are equal, the balloon sits like it does on your desk, and it's just kind of limp, not stretched in any way. That's my guess, and I think that's true.
That feels right to me.
Yeah, it would be. Yeah, it would be. It in my head. I'm imagining like a sock or like a net or something like that, and like you could put a knot on the end of a sock, but the air can go in and out to equilibrate the pressure inside and out, and it's just always going to be just this limp thing, right?
Right.
That happens to have a knot in it. So the balloon being equal pressure inside and out, it's just going to sit there like a sock, or as though it had holes in it.
Right. So yeah, there's no way to inflate it and have the pressure be
right.
Yeah. So I think either way, we're at the point where we're ready to say, okay, the pressure inside the balloon is greater.
Yes. All that to say, the pressure inside of a balloon is greater. What about a little bit of a side topic? How about a bubble, like a soap film bubble?
I think it's also greater because
I think so too.
The surface tension. It's the same sort of concept, just a little bit less.
Right. I mean, yeah, like a little kid's bubble with the wand that you do blow into it, just, like a balloon kind of, and it seals itself.
Yeah.
And I'm imagining, like, I just was at the park and there was a guy with the big rope bubble maker. Have you seen those?
Uh-huh.
And yeah, like imagining what that guy did, he just kind of held it up, and the wind, I guess, was enough to blow to increase the pressure inside the film of soap, and then it closed itself, and it was a bubble.
Yeah.
So it's just barely higher than atmospheric pressure just to kind of keep the bubble in its shape.
Yeah, there's not a whole lot of compression that needs to happen to fill it. So
Right.
Which is why, like, I was thinking about, I was like, oh, okay, I need to come up with an example of something you can fill with air that wouldn't change. And my first thought was bubbles, but then I said, oh no, bubbles just a balloon. That's why I came up with like kind of the trash bag thing, where there's no, you can just like, you could imagine blowing up a trash bag and sealing it, but it's not like, don't inflate it all the way, because it's going to keep its structure independent of, like how much air in there, and until you start to like blow it up till it starts expanding.
Yeah. So before we get to the other balloons, I think we have something interesting with the trash bags. Think about, or maybe we can go straight to balloons, but I want to think about the weight of the balloon itself and how that affects it. And I have a feeling we're going to get there, and that's kind of how it maybe affects the answer of what we thought the obvious answer was. But imagine a balloon with a weight on top of it. Like the balloon is inflated and it's holding up a weight.
Okay.
That makes sense?
Yes. Yep.
So there's like kind of a little dent where this weight is sitting on a balloon. The air inside the balloon without the weight, say, is at 2 atmospheres, just to get numbers. You put a weight on it, what happens to that pressure inside the balloon?
I think it goes up, right?
I think so too. So you have an atmosphere or a 2 atmosphere balloon, put a weight on it and say that now the air inside, you're compressing it, right? Essentially So say it's 2.5 atmospheres.
Okay.
If you pop that balloon, the air that was compressed at 2.5 atmospheres now is expanded to 1 atmosphere. And so it takes up a lot larger volume, right?
Right.
I think that's kind of what we're getting at with the balloon in the balloon, is my guess.
Yeah. So I think that's kind of where it's going. So we can say now that a balloon has a higher pressure than atmosphere, right?
Can we generalize? Can we generalize that to say a balloon has higher pressure inside than it does outside?
Yes.
Okay. So going to the actual GIF with the balloon inside the balloon, does that necessarily mean that the inner balloon is higher pressure inside than the outer balloons inside?
I think it does.
Okay. I think you're right. Because if the inner balloon was less pressure than the outer balloon, the inner balloon would be squished. Until, well...
Yeah. Do the pressures... Does it get to some equilibrium?
That's what I was just thinking. Like if you have a balloon, ignore the balloon in a balloon and just put one balloon in a room and start increasing the pressure in the room.
Mm-hmm. The balloon, yeah, it's gonna...
Is it always going to have higher pressure, the balloon, than the room itself? I think so.
Right. Well, that's what I was trying to get with the walking down Mount Everest with the balloon. Like, you increase the pressure of the surroundings. What happens inside the balloon? I think it goes up because it also is being compressed, by the same pressure.
Yes, I think that's true. Okay, so all of that's to say that inner balloon is higher pressure than the outer balloon.
Yes. So then
that seems weird. Like you blow up a balloon and put it in a balloon. I guess I didn't see how they put the balloon in the balloon.
Yeah, I think you'd have to do it when they're both uninflated.
Oh, they do kind of show it. They blow up the outer one first and have the nozzle of the inner one sticking out still. Okay. And then they blow up the inner one.
Yeah.
So by the act of blowing up the inner one inside the outer balloon, you are making the pressure inside the inner one higher.
Right.
You have to in order to inflate it. That's the only way you can inflate a balloon is to increase the pressure bigger than its surroundings.
Right.
Okay. I don't know why that was so hard to think about.
So then when it, just like you said with the kind of the weight on it, I guess when you pop the inner balloon now, that gas is going to come to some pressure. The whole gas of the one balloon that's left over is going to come to some equilibrium pressure. That's not the pressure of the white balloon or the black balloon, but somewhere in between.
So just to reiterate, there is a black balloon is inner balloon. Black balloon inside, white balloon or transparent balloon outside.
Yeah. So you pop black balloon. It has a higher pressure than the outside transparent balloon. So then that gas is going to expand because it's at a higher pressure until the whole system comes to some equilibrium that's somewhere in between. So, but there is some expansion that's happening, right?
Yeah, it has to expand. Because it was at a higher pressure, and now all of a sudden that air is released into a lower pressure. But it's still sealed, and it's still got the elastic outer balloon keeping it trapped. So the pressure does go up. And so I think the outer balloon expands a little bit.
Yeah, it almost doesn't look like it in the video, but I think that's got to be the...
You can't really tell, but I think that's true.
And that was a Foolish Chemist was the Reddit user that he essentially went through that whole thing. I hadn't quite walked through it. I just read some stuff about pressures and I was like, oh, wait, yeah, I think there's a little more here.
Foolish Chemist was the answer, the first your top voted answer.
Yeah.
Okay. I didn't read that, but I just saw the question and I was like, well, it's kind of boring. Obviously, the volume's not changing. It's just air, contained, and then now it's not contained. But yeah, obviously didn't think about it enough. Yeah,
that was kind of my thought. Too. Yeah, it was like, no change. But I think, okay, there's some, you gotta use the ideal gas a little bit.
Mm-hmm. Yeah. And it's funny because like the actual physics, or, what seems like the actual physics is, absorption of a black surface warming up to the point of of tearing the black balloon, whereas the white balloon or transparent balloon, well, it starts off white, and then when you stretch it, it's transparent. The light just passes through; it doesn't get absorbed, so the white balloon doesn't heat up, and that's how you pop the inner balloon.
Ooh.
Which seems like that's the physics question. It's like, how does that work? But
Ooh, wait, but okay, since you brought it up, is that how it works?
That's my quick explanation.
Because that was my original thought too. Was like, oh, okay, like the blacks can absorb more. But I would say that would be 100% true if they were using like a laser. But the fact that they're using a magnifying glass to focus the sun, I'm curious is if you were to focus the sun onto the white balloon, if it would still pop it.
I see what you're saying. It could be both. Could be a combination of both.
I mean, clearly, if it was utterly transparent, it wouldn't pop, even if you focus the beam on it, because the light would just pass through, wouldn't get absorbed.
Right.
And that might be the case with this balloon too. Maybe it just can't absorb enough heat to pop, but they don't really show that part. I feel like though the demo of a black thing absorbing more energy than like a transparent or whitish sort of thing would be better demonstrated with a laser.
Yeah. Or you could use the magnifying glass to first focus on the white balloon and show it won't pop. Or maybe it would. I actually don't know. Maybe it would.
Yeah, I think it would depend on the properties of that balloon.
Yeah.
Or that material, I guess.
Mm-hmm. Yeah, so the surface of the black balloon, the inner balloon, is a few inches from the surface of the white balloon. So they're focusing with the magnifying glass, they're focusing on the lower inner balloon's surface. Yeah. Actually didn't think about that, but you're right.
It's a pretty interesting little visual that, when presented, just seems like very obvious and straightforward. I feel like of nothing interesting is happening, but then a little more thought, and I was like, oh, and then foolish chemist also pointing out that pressure is important.
Yeah, interesting. So get yourself a black balloon and a white balloon, blow them up, the black one inside the other, and take a magnifying glass. See if you can measure a change in volume of the white balloon when the black one pops. Yeah.
If you really wanted to get into it to do the full experiment, put it in water. You use water to displace it to measure the volume of the balloon.
Before and after.
Yeah. You just have to do it either with air temperature water or so fast that the temperature of the balloon doesn't change. Mm-hmm. That's how I would first try it, at least.
Yeah.
If you imagine doing this with trash bags, not fully inflated trash bags, I think I would say that the pressure isn't going to. Maybe another way to think about it is if I took a big mason jar I take a small mason jar and I seal it. And then I take a bigger mason jar and I put the small one inside of that one, and then I seal the big one. So I have two mason jars, one inside of the other, both sealed. And I somehow broke the inner one. I don't think the pressure is changing inside of that.
No, if the pressures are the same in both, it shouldn't. If the pressures were the same in both to begin with. Yeah.
Right. So I think it's just it's
a consequence of the pressure being bigger in the inner balloon.
Well, yeah, and the reason that it is that is because it's like this rubber material that it's putting its own force back on the air.
Right.
Cool. All right. Do you want to talk about another thing too?
Yeah, I think we covered that GIF pretty well. On an unrelated topic, something I've always wanted to look into, and I don't know, I've seen it in physics questions in textbooks, but never really taken a deep dive into it, is a sweet spot, like on a bat or a ball, a golf club or something like that. Let's talk about a bat. I don't really want to get into a golf club. It's a little bit more involved, I would imagine. But what is the sweet spot on a bat? Right.
Well, also, I think this could lead us to an interesting question that I'll pose maybe a little bit later, but it's something we've talked about before off podcast.
Okay.
Yeah. So the sweet spot, right, is you've all if you've played softball or baseball and you've hit the ball, every once in a while you hit it and it hurts your hands so bad.
Yeah, you get that sting.
Yeah, it is not a comfortable feeling at all. The sweet spot is the exact opposite of that.
Right.
It's the time when you hit it and you feel nothing.
Right.
It's just, there's no force on your hand.
Yeah. So it took me a while to realize like what's causing that sensation and what, like how you would define physically what's happening. But imagine you're swinging a baseball bat and you hit the ball somewhere that pushes back on your hands, basically, as you're swinging. You're basically going to have to use the force of your hands to move the bat as you're swinging it, but then also fight against the ball. Like it's imagine your hand basically slapping the ball without the bat there. That's that feeling. That hurts a lot. So you're getting this like extra rotation. One's the rotation of the swing, but then you're getting a second kind of rotation due to the ball hitting the bat and it kicking back in your hand.
Yeah. And so this is kind of the question. This is a good way for me to introduce the question that we've kind of discussed before. It's like if you imagine if you had a ball in space and a bat in space and you shoot the ball at the bat and it hits it somewhere not in the middle, or not, just so, anywhere along the edge generally, the bat will do some amount of like spinning and moving potentially. So yeah, it has this extra, that's that extra rotation that you're talking about, is it'll start kind of doing a spin instead of just a translation, but also it'll start moving. If the ball is moving to the left when it hits the bat should also be moving slightly to the left afterwards, right?
Right.
Which is also the question that we've asked before is, if you have a meter stick in space and you throw a ball at the 50 centimeter mark or the 25 centimeter mark or the 0 centimeter mark, like what happens, along each different spot when it hits?
Yeah, so it's easy to start with the center one, and let's assume uniform mass, uniform density in this linear object, just to keep it simple. But it works in general in any sort of irregular shape like a bat, which is certainly not uniformly distributed. But say you throw a ball at the center of mass of the object. For the meter stick, if it's uniform, just the 50 centimeter mark. So you throw it at 50 centimeters, what's going to happen?
It's going to now act like 2 point particles colliding, 2 billiard balls. So if you hit the 50 centimeter mark, then, there's some collision physics that happens where total momentum will be conserved, but the ball is going to, what's the easiest? Let's say the meter stick weight as much as the ball. The ball is going to stop, the meter stick will start moving. Just like when a billiard ball, the cue ball hits a ball, if it's the right hit, no spin or anything, it's going to stop and the other ball is going to.
Right. So the key thing is if you throw it and it hits the center, it's not going to start rotating. The meter stick's just going to translate. 100% translation, 0 rotation. Right?
Yes.
Yeah. So meter stick's moving sideways. It's still, upright is my picture of it. And it's just going to keep moving that way without rotating at all. Now, the interesting thing is thinking about what happens when you throw the ball and say you throw it at the 0 centimeter mark. Say that I'm imagining that it's at the top, the 0 mark.
Okay.
It doesn't really matter, but throw it at the top. What's going to happen?
I mean, like my intuition says it's going to hit it, and now the ruler is going to start spinning, or the meter stick's going to start spinning, and the ball's just going to continue on its merry way. I mean, I got to imagine there's probably some small amount of translation that happens, but ideally most of it's going to be spinning the meter stick.
I think you're right. I'm not sold that it continues, that it only continues. Like it's possible for it to bounce back. Like if the meter stick was the Empire State Building in space and you threw a baseball at it, the baseball would bounce back, right, and the Empire State Building would start rotating a little bit.
Okay, yeah, I can see. Yeah.
So there's some, question of how it would actually end up. Would the ball keep moving forward or would it not? We do know 2 things have to be conserved. Well, I guess let's work with 2. I don't think we need energy. Well, energy is certainly conserved, but kinetic energy not necessarily. Momentum and angular momentum. Both those 2 things have to be conserved.
Right.
And I'm saying we don't need kinetic energy conserved because the energy might go into something else, sound or something like that. So my main point in thinking about Empire State Building is angular momentum is conserved, certainly, and linear momentum. So angular momentum wise, the ball moving forward, it's all of this angular stuff is with respect to a pivot point or an axis of rotation, right?
Yep.
So you got to pick your pivot. I kind of remember you and I talking about this a long time ago. I was arguing that you could pick anywhere to be the pivot, the axis of rotation. Is that?
That sounds right.
Yeah. And then we got kind of it stuck, right? When we did that, because we said if you picked the location of contact between the ball and the meter stick, how much angular momentum is there initially?
0.
Right.
Because, yeah, I mean, maybe that's a point worth discussing slightly too. Let's say you pick any other point. Mm-hmm. So say you pick the center of the meter stick. Mm-hmm. The ball is moving at it. The ball's not rotating around it, but there's still an angular momentum there that's happening because it's moving off axis.
Right.
Which is, if you're not deep into physics, that might sound weird or wrong, but it's true.
Yeah. Well, the equation that's in my head is angular momentum is R cross P, two vectors, cross product. R is the distance from the pivot point to the object that's moving. P is the momentum of that object. So when the ball is striking the end of the meter stick, right before the collision, the ball is half the meter stick away from the pivot point, which is the center.
Right.
And it has some momentum. It's moving with some speed and it has mass, right?
Yes.
So you got the momentum mv and you got the distance r. That's a non-zero angular momentum initially.
Right.
So you got to end up with the same amount. But the problem is it's not a problem. The weird thing for my head to wrap around is when you pick the pivot point to be the end of the meter stick, the place where the ball is striking the meter stick, then you initially have 0 angular momentum.
Right.
Because the R, the distance from the pivot point to where the ball strikes, that's 0. So now your angular momentum of R times P, R is 0. So you got 0 times P. That's 0 angular momentum initially. So does the meter stick start spinning? So, okay, the stumping part in my head is we picked the pivot point to be where the ball struck. Initially 0 angular momentum. Final has to be 0 angular momentum, but we know the thing rotates because if we picked a different pivot point like the center of mass, non-zero initial angular momentum, non-zero final angular momentum, which I believe comes about from the rotation of the meter stick and the ball doing whatever the ball is going to do. Maybe it continues forward, maybe it bounces back, maybe it completely stops. But the fact that we have a final angular momentum of 0 and the thing spinning is where I'm getting stuck. Like the bat doesn't care what pivot point you chose, or the meter stick doesn't care what pivot point you chose. It's just going to do whatever it does, right? Like you took a video of it. It's not like, oh, this is the video with us thinking about the center of mass as the pivot point. This is the video thinking about the end as the pivot point.
Right. Yeah. It's the same video.
Yeah, exactly. So what happens? It's 0 initial angular momentum. Let's say in the video, the ball, we just set it up perfectly so that the ball stops.
Okay.
What happens to the meter stick? How does that lead? How does the meter stick spinning, which I think we both agree is going to happen?
Yes.
How does that lead to 0 angular momentum final?
Right. About that pivot point, the contact pivot.
Right. Maybe it's, I don't know. Okay, here's a maybe separate question that might help answer this. Does the meter stick translate? Is there translational motion of the meter stick?
Yes.
I think so too.
So,
yeah, I think you and I both hit it at the same time. Yeah. Yep.
Yeah, that's got to be the case in order for there to be no angular momentum, because now it's a traveling mass with respect to our chosen point.
Right. And yeah. And I'm visualizing the right hand rule. I'm treating for the linear translational motion part of this. I'm treating the meter stick like a point object at its center of mass. We could work it out for the continuous object, but I think it's valid to just compress the meter stick to a single point and just treat it like that single point is translating.
Yeah, I think so.
So if we threw the ball at the top of the meter stick, the center of mass of the meter stick is going to translate. Say the ball started from the left, it's moving to the right, hits the top of the meter stick. The ball stops because we set up the mass and moment and velocity and all that perfectly. Ball stops. The center of mass of the meter stick continues, just like we said if we threw it at the center of mass of the meter stick, right?
Yeah, it must be moving at some speed now because linear momentum needs to be conserved.
Right. So we have an R from the pivot point to the center of mass of the meter stick that points downward.
Right.
We have a P, the linear momentum of the meter stick to the right.
Okay.
Good with that?
Yeah. Sorry, our pictures are reversed, but I'm following now.
Okay. Yeah.
My ball was coming in from the right, but you're saying
no.
the ball's coming in from the left. Okay.
Yeah, I was imagining ball coming in from the left. Ball coming in from the left, the meter stick is going to be moving to the right after center of mass of the meter stick's moving to the right after the collision. So R cross P, the angular momentum due to the linear motion of the meter stick with the right hand rule points which direction? R is down, P is to the right.
Yeah, up, I guess, or
like towards us.
Yeah.
Or
if we're looking down on it.
Yeah, out of the page if you're drawing it on a sheet of paper.
Yes.
So down cross right is out towards us.
Right.
Good?
Yeah.
Okay. Which direction is this thing spinning? Like it's rotating.
It is rotating clockwise.
Clockwise. So which direction is that angular momentum?
Down
or in or away from us. Yeah. So we have two opposite angular momentums, one due to the rotation and one due to the linear translation of the meter stick. That's the cancellation that gives us zero final angular momentum.
Yeah. So the two angular momentums, okay. I don't know why it took so long to figure out, but the two angular momentums are canceled because now the meter stick has to be moving.
Right. And rotating, and those two things combined give us zero. And the ball could be doing whatever the ball does to make sure it's zero, but we can ignore it. Like we can say it stops, so it has zero momentum after the collision, just to make it simpler.
Yeah, but then if you think about it a little bit, though, just to be a little clear, is when the ball hits the center of the meter stick, and let's say it also stopped, we can instantly say that the meter stick has the same mass as the ball, right?
Yes, because of the conservation of linear momentum. Yep.
Yes. Yeah. But now when it hits the top part of it and it stops, you can't make that same assumption because now, you have these two other momentums that are canceling and it's going to be moving. Let me think about it. If they were the same mass in that case, when it hits when the ball hits the ruler, I don't think it's going to stop in that case. I'd have to fully work out the math, but in order for
I think it would have to have the same mass in order to stop.
No, because if it has to be translating, which we know is true, right? When it hits the top part, then if it stops, that means now the bottom or it's moving now at the same velocity as the ball. Okay, God, I have to. My thoughts are leaving me. I had this formed and then it's fleeting.
I'm literally thinking about the linear momentum conservation equation only, and I think that alone tells us it has to be the same mass if the thing's to stop.
No, because I think some of it can be some of it can be taking up and it's a weird. I don't know exactly how to phrase this. If it stopped, now it's translating. All right. I guess you're right. But if it has a bigger mass though, it can be moving slower, right?
If what has a
but then it's going to recoil. Potentially, if it hit the center, it would.
If what has a bigger mass, the meter stick?
Yeah. But then
the ball would recoil, would bounce back.
See, that's the part I'm unsure about. I definitely agree that happens when it hits the center.
Okay.
That it would, if they're the same mass, it would stop. If the meter stick had a larger mass, it would recoil. But I'm not sure about if it hits the top of it. Because I'm wondering if there's some.
I agree. It's not as intuitive, but I think the conservation of linear momentum tells you it has to do that.
Yeah, I'm with you there, but
Like if you don't think about it too much, it has to do that. But if you think about it a little bit more, like, oh, what if it's really fat at the end that it's hitting? Yeah, or thin at the end that it's hitting, or whatever.
Or I mean, I'm just thinking. I know. At the end, the linear momentum has to be the same as the start.
Mm-hmm.
But I'm thinking, is there a situation where if it has a larger mass, let's say, it's now moving slower, but the ball hasn't recoiled, but instead now the thing starts spinning? In a collision equation, what makes the ball have to recoil in the first place? It's a conservation of energy if it's an elastic collision? Is that right?
Yeah. We're assuming perfectly elastic collision. I think that's the underlying assumption in all of this that we haven't really said, but yes.
Okay, let's start there. Let's say, okay, we have an elastic collision, no energy's lost. If the ball's moving, it has some kinetic energy,
mm-hmm.
it hits the meter stick that weighs the same, has the
mm-hmm.
same mass.
Mm-hmm.
Through conservation of energy, the meter stick can't be moving at the same velocity that the ball was if it hit the top, because now it's also spinning.
Right.
So there's rotational energy there, and there's translational kinetic energy.
Right.
I guess, yeah, I think that's why I think if it was the same mass, it wouldn't stop. Or maybe the meter stick has to be heavier in order for if the ball stops. Does that make sense?
Yeah. And what I'm picturing in my head is imagine like instead of a meter stick, imagine weights like a dumbbell, like really huge masses at either end of this thing. And it's an equal mass slams into one of the ends weights.
So like half the mass of the dumbbell.
Yeah.
Is that what you're saying?
Yeah.
It hits it. Okay.
Is that a different situation than cutting the dumbbell in half, putting the weights in the middle and having the little bars sticking out of the ends, and then half the mass hitting that end of the dumbbell? So that the most of the weight's concentrated towards the center now rather than the outside. Like basically all we've changed is the moment of inertia. Does that affect what happens to the weight, like the ball coming in?
Sorry. Okay. Let me see if I can rephrase back at you.
Mm-hmm.
You have one mass that weighs a pound.
Mm-hmm.
And then you have two other masses, each one weighing a pound, and they are connected by some weightless rod.
Yep.
Are you okay with that?
Yeah.
That way. Okay. So you're wondering if when the mass comes in, if the 1 pound mass comes in and it hits, man, I'm trying to see if I can give a better auditorial description of what I'm saying, because I used 1 pound too much, I think. I don't know. Does red and blue work? We have a red 1 pound mass and two blue 1 pound masses that are connected by a weightless rod.
Okay.
So the red mass comes in and it hits one of the blue masses.
Yes.
And you're wondering if that is how that interaction is different than if one of the red masses just hit one of the blue masses completely by itself, not attached to anything?
No.
Is that what you're asking?
No.
Okay.
I'm asking, so the first part is correct. Red comes in and hits one of the blues, which are at the ends of this massless rod. Okay. Right? Now slide the blue masses to the middle of the rod. So, but the rod still exists. It's still like stretching out. We just ignore that it has mass.
Right.
Do you have that picture?
Yes. Yeah.
Yeah. So now send in the red mass and it hits the end of the rod with the blue masses at the center now.
Oh, gotcha.
Does that affect the recoil of the red mass? Does the moment, like the distribution of the mass, does the moment of inertia of the blue, like the what we started calling the meter stick and then we started making it more complicated, does that affect the recoil of the incoming object?
I think it does.
I think it does too, and I'd have to write out a few equations to prove it, but in my head it does.
Yeah, I mean, because in this situation, especially if we're doing the elastic one, there's 3 things we have to worry about, or I guess 4, right? We have to worry about conservation of linear momentum, conservation of angular momentum. Yeah, I guess 3. And then conservation of energy if it's an elastic collision, right? So I think essentially the way those 3 things will balance out is, like, I imagine what might happen when the red mass hits the blue mass at the end of the rod, you might get like a slower rotational, like it might spin less than if it hit it the other way. It might spin more, or maybe that's exactly opposite or something like that. Yeah, I'd have to write it out to know exactly. But yeah, so I think, in the end, I don't know how to say it without going into more precise detail, but the angular momentum and linear momentum and energies all can work out in like a few different ways that we get situations where the red ball recoils and then now it's spinning fast but translating slow, or or I guess it'd be translating faster. It'd have to be translating faster. But yeah,
we got into this discussion because we weren't positive how the recoil would happen. Like, is it enough to just say, oh, the masses are equal, then the ball is gonna stop after it hits it? And I think I said yes initially, the masses have to be equal, but you were kind of like, no, I don't think so. And so we got down this rabbit hole of changing the object a bunch to see what would happen. And I think the end result is it depends on a lot of things. It's not as simple as two billiard balls colliding. Like, it's a little more complicated than that.
Right. But I think you can say that they won't be equal masses though if it starts rotating. If the red ball stops, I don't think it can be equal masses, because
I think that's true. And that's where I was wrong earlier. Exactly. Okay.
So all this back to get to the sweet spot.
Yeah. What is the sweet spot? So the sweet spot is where you would throw the ball in order to not have your hands sting. But what does it mean to have your hands sting? That means like the end of the rod that you're holding, you want that to be motionless after the collision. Does that make sense?
Yeah. So you want it to not try to rotate in your hands. You don't want it to wiggle in your hands, essentially.
Right.
Is that right?
That's right. You don't want your hands to have to push against the bat at all after the collision with the ball happens.
Yeah, or you want to minimize it, right? Because you definitely have to push against the bat some amount because you're changing the ball's direction.
Right. Yeah, no, definitely.
Yeah.
And, there's the swing involved, but just the idealized situation of here's a meter stick, throw a ball some distance from, let's say from the top, throw a ball at the meter stick, some distance from the top of the meter stick. At what mark on the meter stick do you want to throw it so that the top of the meter stick does not move?
Right.
Even though the rest of the meter stick's definitely going to be moving, we can figure out where to throw it so the top of the meter stick doesn't move.
Okay. All right. Actually, okay. I was a little confused then. No, okay. I see what you're saying. I was thinking that we just didn't want the whole thing to rotate. Like,
no.
Translation was fine, rotation was bad. But no, you're saying, okay, we don't want it. We want to pick a spot somewhere on the meter stick and say that spot right there, don't move.
Right. Exactly. So if we pick the spot at the end of the meter stick, where do we throw the ball so that the meter stick's going to slide to the right and the top of the meter stick is going to rotate to the left in equal amounts to exactly cancel out at the end of the meter stick. Does that picture make sense?
Yeah, so the center of mass, kind of based on our previous discussion, we know it has to start moving.
Right.
Right.
That's right.
And we also know that if it's not hitting the center of the meter stick, it's going to start rotating. So there's a way such that those two things cancel out right at the top of the meter stick, that those two motions negate each other only at that one point.
Right.
But that's the point that we care about. That's where our hands are.
That's where your hands are. That's where the ball hits. That's the sweet spot. Does that make sense?
Gotcha. Yeah. So that I mean, without doing a whole bunch of math, I think we know just in order for that thing to happen, it's got to be greater than or past the center of mass, right? Like,
yes.
If we're saying 0 is the top of the stick, it's got to be further than 50%.
That's right. Yep. It depends on a few things. And the textbook version of this problem usually makes assumptions like the ball and the meter stick are the same mass, so that M drops out and you get, something nice like 2/3, 2/3 the length.
Right.
But if we put in a mass of a baseball and a mass of a meter stick or a, baseball bat, and an odd moment of inertia that's not a nice, 1/12 ml squared or something like that, it gets more complicated, but you can work it out.
Yeah, there's there's another term for this as well that you can Google called the center of percussion,
right,
or the center of oscillation.
Right. Yeah, so you can look up center of percussion, see some good engineering and physics discussions. But that's essentially what you're doing. You're trying to figure out where do you hit the thing so that whatever point you're interested in doesn't move after this collision happens.
I remember there being something interesting about this I'm trying to read. So here, I'll just read it off of Wikipedia. I think maybe you'll be able to make sense of this. Okay, the same point is called the center of oscillation for the object suspended from a pivot as a pendulum, meaning that a simple pendulum with its mass concentrated at that point will have the same period of oscillation as the compound pendulum. Okay, I get it, I think.
The center, the mass is concentrated at what we're calling the sweet spot.
Yeah. I see. So how do you find the sweet spot of your bat? Essentially, is kind of what this is answering. And what you do is you hang it from the end, or really, I guess the most ideal thing is you'd hang it from wherever your hand is,
right? And
you displace it by some angle, and you let go, and you measure the period, and figure out how long, what its oscillation is. Then you get a regular pendulum that's just like a ball that weighs as much as your bat does, and you change the length of it until it moves at the same period.
So I think you made a little mistake there.
Ooh, okay.
What's the period of a simple pendulum?
Square root L over G? G over L?
Well, yeah, angular, I guess, omega, the angular frequency. Let me ask a different way. What is not in that equation?
Mass.
Yep.
Yeah, all right. Yeah, so I guess it doesn't matter what the mass is.
It doesn't matter what the mass is. It doesn't have to be the same mass as your bat.
Yeah.
Just any simple pendulum. But what it does depend on is the length, right? That length thing is what we're trying to find.
Right. Yeah. So, okay. Rephrase. You just get any ball.
Yeah.
You take your baseball.
Right. Okay.
And you hang it, and you keep adjusting the length until it oscillates with the same period that your bat does.
Right. And that length is the distance from your, whatever you're hanging the bat from, and the sweet spot, or what center of what? I know percussion, but what's the one you were talking about?
Center of oscillation.
Center of oscillation. Yeah. And I kind of looked it up briefly just before recording. Some interesting things came up, like thinking about the word percussion, center of percussion, different harmonics come into play. Like if you look at the vibrations inside the rigid, I guess not rigid, but flexible object, there's different places where nodes and antinodes occur. And the sweet spot is somewhere in particular where you get some really nice amplification, I think, of harmonics. Would you think it'd be amplification of harmonics or like deadening, like zero, like all cancellation happening at the sweet spot?
I think
those are kind of fuzzy terms. I don't even really know what I'm asking. But as I said it, I was thinking like, wait, do we want more vibration or do we want less vibration at the sweet spot?
I don't. I think the thing is, I think you want a node at the pivot.
Yeah, you definitely want a node at your hands. That's for sure. So where do you hit it such that you get a complete cancellation at your hands? Yeah, that's a good way to think of it.
Yeah, and I'm wondering if is that the same point, that the sweet spot is also that spot?
I think so.
I'm trying. Okay, wait. Maybe we can think about like if we thought about like a rod or a meter stick or something. Its modes are going to be, just like a natural, node at each end, right? Would be like, a half wavelength, then like one wavelength, and so just integer number of half wavelengths in there. So when you do any of those, right, there's essentially a bunch of places where there's, I guess I don't know how the location of, I'm imagining like playing a guitar. I don't know how
I was just gonna
the
get into
location of like strumming, where you strum, affects the sound that comes out.
So I think I can get into this. So two things, one step, and then we'll get to the guitars. The first step is just imagine the physics demo of the taut string, and you turn on the little oscillator and it starts vibrating the string, and you see the nice antinodes, right?
Yeah.
the big humps of the string, but then you get those nice nodes where there's no movement at all.
Right.
If you pinched a node, it wouldn't really affect what's happening, right?
Yeah, I don't think so.
So I'm imagining you're like, that's where your hands are on the bat, is at a node. And if you like dropped a baseball or plucked the string at one of the antinodes, it wouldn't affect your hand. But if you put your finger on in an antinode where it's oscillating a lot, you could hit that, you would feel it on that finger quite a bit.
Yeah, you feel like some sort of vibrational.
Right. But your hand that's gripping the node wouldn't feel it at all. Wouldn't know anything was happening. So now going to the guitar string, imagine playing a harmonic. Say you're playing a harmonic on the 5th fret.
Okay.
And does that split? I don't have a guitar around me. If you have one near you, do you have one near you? 5th fret, I think, splits the guitar string into fourths. Is that right?
That looks about right.
Yeah. So a quarter of the string is between your finger and the nut. Is that true? Like about there?
The head, where the...
Yeah, the head, up towards the tuning pegs. Yeah.
Yeah. Yeah, that's what I'm looking at. That looks about like a quarter of it.
The 12th fret is dead center of your string, right?
Yeah. Okay, so I just measured, and one other length leads me to the 12th fret. So.
Okay, cool. So play a harmonic on the 5th fret, but then picture the string being divided into quarters.
Mm-hmm.
If you plucked the string trying to play the harmonic on the 5th fret, there's going to be a node at a quarter of the way, half the way, 3/4 of the way, and then the other end of the string, right?
Right.
So there's the two ends of the string are nodes, but then there's 3 nodes on the string itself.
Yeah.
So by putting your finger there to play a harmonic, you're making a node on the 5th fret. There's 2 other places where there's nodes. That means the string isn't moving in those places if you were to play that harmonic.
Right.
One of them is the 12th fret.
Yep.
The other one you're just going to kind of have to eyeball. But I bet if you went to pluck the string at either of those places, you're not going to be able to play that harmonic, or it's going to be really dead sounding.
Yeah, so we can do it real quick, maybe. I don't know. Have you been able to hear it at all?
I can kind of hear that you have a guitar, yeah.
Okay, all right. Well, let's see if this comes through. Okay, so I was just the pure harmonic. Let me try one. Okay, now I'm going to try plucking it at the 12th fret. Yeah, it's a lot.
It's
a lot deader.
It sounds pretty dead. Yeah, and then try plucking it at an antinode where the string's vibrating a lot.
Yep.
I mean, I can barely hear it, but it sounds a little better, right?
Yeah, it definitely does. Hopefully it'll come through a little better when I amplify it. But yeah.
But I think that has to play a role in this sweet spot discussion, in that you're gripping the baseball bat at where you're playing a harmonic, essentially, some node, and the baseball is hitting an antinode. So you can get a lot of vibration out of the string, but your hands don't feel it at all. Or that the bat can move a lot and transfer a lot of its energy to the ball, where your hands don't really feel anything because they're in a node. That's my impression of what's supposed to be happening.
Okay. So you're saying the ball is going to be hitting a node. Is that right?
No, I think the ball's hitting an antinode.
I could see an argument for both. I guess
I could too. Actually, I could,
because it seems like if it's hitting an antinode, you just don't get a lot of vibration in the object itself. You pluck the dead.
Right. But I think you want the bat to kind of flex and bend and really snap back the ball to send it flying. You know what I mean?
Well, I feel like the vibrations essentially, like the center of mass of the bat on average is along this, the axis of it. Even if it's vibrating in like a harmonic way.
Right.
I feel like if it hit an antinode, let's say, and it didn't cause, I don't know if this is true. I'm assuming if it hits an antinode, it's not going to cause much vibration in the bat because of that little guitar demo.
I thought it would cause a lot of vibration.
Oh, sorry. Did I say antinode?
Yeah.
I always get these.
Yeah.
I mean, I know what's what. I just always intermix the two words.
Yeah.
Yeah. Okay. Sorry. If it hits a node,
yes,
it's not going to get much vibration based on the guitar demo there.
But we're ignoring the other harmonics. But You know what I mean?
Yeah, I guess that's true.
It's like you're exciting different harmonics that might hit your hand.
Right.
Because you're hitting a place where there's like your finger, your hand is going to get thrown about because it's no longer at a node for this disturbance that's happened on the bat.
But okay, maybe this will help. Okay, so a rod has a center of percussion or sweet spot 2/3 the length of the rod.
Right. If you worked out all the math we talked about with like certain assumptions, like equal masses and all that stuff. Yeah. 2/3 is the answer you'd get for where the sweet spot is.
Yeah. So that is a node of one of the normal modes of oscillation of the rod, right? Or actually, because it's free at both ends. I don't know. Is it free at both ends?
I would imagine for a bat, you'd want it to be fixed. And like, yeah, I don't know. We kind of started by talking about a meter stick in outer space, but then the real definition depends on like hanging the thing from an end. I don't know. Honestly, I don't know.
Because I'm imagining, okay, if it's like the waves on a string thing, like we were talking about earlier, 2/3 of the way is an anti-node for one of the normal modes of it, which would mean it would be hitting an anti-node if it was a rod. Or sorry, I just did it again. It'd be hitting a node. 2/3 of the way of the mass is a node.
Is it?
Yeah, because that cuts it into thirds, which is, you can fit 3 half wavelengths.
That's one of the harmonics that, you could make, you could make a harmonic with the node at 1/3 of the way. I mean, you can make a harmonic with a node at any place, right?
No, I don't think, right? It has to be, the nodes all have to be, if both ends are fixed, which I'm still not convinced that's necessarily
let's go with the guitar string and Yeah.
I mean,
ends are fixed.
You can hit a harmonic at any integer multiple of half wavelengths. So there's definitely,
But a third isn't an integer multiple of a half wavelength.
Oh, let me think. Yeah, okay.
I think you can make a harmonic anywhere, and it's just that cutting it in half is really loud. I mean, the loudest is just open string, right? The fundamental. Then you cut it in half. That's a pretty easy harmonic to play. It's pretty loud. Cut it in thirds with the 5th fret. That's another one that's super easy to play.
Or 7th. I think it's the 7th fret.
Oh, 7th fret. Yeah, it's cutting in thirds. And then 5th and 7th frets are really easy harmonics to play because you're cutting it into thirds and quarters. But you can play harmonic on the 9th fret. I mean, you can play false harmonics, which are like, have you ever played those?
Like a pinch harmonic?
Yeah, pinch harmonic. That's basically cutting it into like tiny, tiny numbers, distance between your thumb and your pick.
Okay, all right.
I think you just don't hear them because they're not as, like the little spectrum you'd get of what frequencies are prevalent in the sound. It's mostly those first few.
But I'm trying. Okay, wait. But if you solve, I guess it's the wave equation. You try and figure out where to force a node at either end of it, isn't it? I thought it's only, you have to be an integer multiple of half wavelengths. Is that not right? Or the wave?
Series,
that's what
like
I'm
it goes to infinity. In theory, right?
You're right. I'm saying it wrong.
Yeah.
You have to be an integer multiple of the length of it, right? Is that what it is?
Like the length over an integer is what I was imagining.
Yes, yeah, I think that's what it is. Okay, all right. That what needs to happen. This is the wavelength has to be an integer multiple of twice the length.
Yes,
that's one way of putting it. Or the other way that I was trying to say that I kept screwing up is the length has to be an integer multiple of half wavelengths.
Yes.
So essentially, a third works because you can fit a half wavelength of some wavelength in the first third.
Right.
Then in the second third is the full wavelength.
You have 3 half wavelengths.
Yeah.
Right.
But I don't know if you could still do it anywhere.
Yeah.
Though.
Do we span the number line?
Yeah. That's a.
Now we're getting into like math questions that I'm not very comfortable with.
Yeah, I mean, I feel like
different infinities.
Yes. Loosely, I want to say no because of exactly that we're talking only fractions and you can't build the real line with fractions.
Mm-hmm.
So I want to say no. But, well, I guess the wavelength, maybe that's not a fraction. I guess that could be a real number. Anyways.
Beyond the scope of the discussion.
Yeah. So, but to the bat, I don't know what if it's, or to the rod, that is, it's a situation where one of the states is I guess it's a node that it's hitting. I feel like you don't want the bat to vibrate in general, or you want it to vibrate such that it's creating a node. Okay, we know that if you hold the bat at a certain location, you're going to potentially kind of like force a node there, right?
Right.
Or you hold a rod, maybe it's the easier way to think about it. Then we want the ball to hit somewhere that will either make that spot a node for when the ball hits, or I'm thinking if you're creating some harmonic by pinching it in a certain location,
mm-hmm.
then we want the ball to also hit at a node of that harmonic that you've created by pinching it in a certain location. That way it deadens the whole thing.
So what I'm imagining is picture the string, like the little physics demo string, and you put your finger on a node and you drop something pretty light, like let's say a ping pong ball, maybe it even has to be lighter than that, somewhere along the string. Where is it going to bounce back the hardest? And I think I know it's already like the string is, let's say the string isn't vibrating. If it is vibrating, I think the answer is really obvious. You drop it on an antinode because that's going to kick the little ping pong ball back the hardest.
Right.
But if it's not vibrating, where would you drop the ping pong ball to get it to bounce back?
Well, yeah. So that's why I think what I want for in this case is I'm imagining we need the string to not vibrate. That way it's not taking energy. So if we can make the string vibrate the least, then more energy is going to be available for the ball.
I'm picturing it more like it's elastic, like it's going to absorb energy, but then it's going to give it back. Does that make a difference?
Yeah, I don't know. I think we're in a field of physics that I'm...
or like material science of bats. I don't know.
Yeah.
I'm also picturing, I keep coming back in my head and we haven't said it, is a trampoline. And like, where do you jump on a trampoline to get the biggest jump? And it's the most stretchy middle spot, right? Which I would imagine is the center of percussion of the trampoline, where it flexes the most. Like you don't jump on a trampoline at the edge to get a big jump. Right.
Yes. That I am following and I agree with. I just don't know if the analogy to hitting a rigid object is the same, or like a rigid object. I'm just imagining a tight string, a guitar string or something like that too. But
yeah, I don't know. I think we're running in circles and keep getting tripped up on not really understanding what happens when you hit a ball.
Right. Well, here's kind of my thought. Is it's like the ball hitting the ruler, the meter stick in space,
mm-hmm.
where you have to balance, energy, linear momentum, and angular momentum is, and energy is going to end up being divided between kinetic, translational kinetic, and rotational kinetic energy.
Right.
But it's still conserved. So I'm imagining what's going to happen when a ball hits a guitar string or a bat or whatever, it's going to, the thing is going to flex some amount and then recoil, just like plucking it or something like that. But in order for the ball to absorb as much energy when it's going back on the string, that it should be in a spot that makes the string vibrate the least, because otherwise we're imparting some energy in the string.
Right.
So therefore the ball is going to have less. So I think it kind of doing that bounce effect will happen no matter where it hits on the string,
mm-hmm.
like the stretch, recoil, release sort of thing. Just what happens at the string once the ball has left will change depending on where it hit in the first place.
Right.
That's kind of where my intuition is going, which is why I'm saying I feel like we'd want it to be a node where it's hitting to get the most recoil, although it's probably a negligible amount of energy that gets in the vibrational energy into the bat, I would think.
Yeah. I'm still stuck on my trampoline, and then I'm thinking more about bats and like what they're made out of, like aluminum, like are better than wood because the aluminum really absorbs the ball, and like it's got a lot more give and then give back, like it snaps back more than wood does, right?
Right. Well, yeah. So the collision has a better elastic property.
Right.
Than,
right. And the same, like corking bats, corking wooden bats gives an unfair advantage. So they limit how much you can do that. And I think that's like the squishiness, the elastic properties, like you're saying. So all of that to me says you want to hit a place where it flexes and like is springy the most, which is
right.
An antinode. But yeah.
But I think that it's flexing necessarily. I think it might be independent because, when you say, oh, was this collision elastic in real life?
Right.
You're like, oh, no, I heard sound.
Right.
Right. There was sound energy there. Then essentially what I'm saying is I want the ball to hit the string or whatever and recoil so it makes no sound. That way I'm not losing any energy to sound.
Right.
Ideally.
Right.
So like I think that means it would be, in my head, that means it would be more elastic.
You haven't convinced me completely, but I'm seeing both sides, and I think we're stuck at the like, I don't know, it could be either one.
Right. Okay. Well, so then I think if anyone else knows the answer,
drop us
tweet
a line
at us. Yeah, let us know. Send us an email.
Yeah, sounds good. I'm at Like Tortilla on Twitter and Instagram.
I'm at Zak for now.
The caveat.